Good afternoon, everybody. I'm pleased to introduce Jerry McManus today from Lamont. Jerry got all his degrees in Columbia University and then did a postdoc in Woods Hole with Delia Oppo and Bill Curry and stayed there for about a decade longer, and then came back to Columbia, and where he's now a professor in Lamont. Jerry is a paleoceanographer, and he spent quite some time at sea. He studies mostly paleoclimate during the Quaternary, and today he'll tell us about Atlantic meridional overturning circulation and rapid climate change. Thank you.
Thank you very much, Hagit. Thank you all for being here. When Hagit invited me, she said that I would have an hour and a half time slot for my talk. And I thought, wow, she must have been to some of my AGU presentations. And I probably could talk for an hour and a half, but I assure you I don't plan to. But I will therefore take the luxury of taking a minute to provide just a little bit of context of my connection to Yale. As Hagit mentioned, I'm in my third stint at Columbia. I was an undergraduate, I left, I came back as a PhD student, I left, and I came back. In each of those first two times, as an undergraduate, I visited Yale once. As a graduate student, the very first talk that I gave outside of Lamont was at Yale. And of course, you already know that this is a Carl Tarikian story. It was in a room much like this, maybe even this room. And it was my first talk outside Lamont, as I mentioned, so I was somewhat nervous. And I gave my talk, and for all indications, Carl Tarikian slept through it and then raised his hand at the end. And I thought, oh, I know this old trick. You have your question ready before the talk, and then you can snooze for a while and answer. And instead, Carl said, now let me get this straight. And he proceeded to give a synopsis of my talk that was much clearer and maybe surprising to some of you, much more succinct than mine was. And so I think my first answer to my first talk, to my first question at my first talk ever was yes. Although I may have said, yes, sir, because there was nothing more I could add. I'm afraid I can't hold the promise that I'll be as clear as that synopsis of my talk. But I've had some practice over the years, so what I'm going to show you is some great stuff. And if I don't do it justice, please feel free to stop me and ask a question, and I'll try to clarify. Okay, the work, as almost always, I'm going to be showing others' work. And in this case, it's primarily graduate student Jean Henry, former graduate student Sharon Hoffman, and a former postdoc, Louise Bradmiller, who I've been working with, along with a number of other really excellent colleagues. And many of us have spent time at Columbia Lamont. As it turns out, when I looked at this author list, our single overall connection is all to the Woods Hole Oceanographic Institution, where we've all spent some time. And I'll start with this, what I think of as awful figure. And it's awful not in the science, but only in the color scheme, as I view it. And maybe I'll use this to introduce two aspects that might not be familiar to some of you in the audience. One is that, like many paleoceanographers, paleoclimatologists, most of the time I'm going to show time moving from your right to your left. Not always. So I'll try to remind you when I switch back and forth, but mostly that's how I'm going to present time. And then I'm going to apply the convention that warm is up. And warm is broadly defined. If it's temperature, then it will be warm up. But if it's CO2, it will be high CO2 up. If it's methane, it will be methane, high methane up. When it's the strength of the Atlantic meridional overturning circulation, when it's strong, that will be up. I'll try to be consistent about that. This figure introduces the idea that during the last ice age, there was a bipolar contrast in the behavior of the southern hemisphere and the northern hemisphere. And you can see that in almost any location here, but if you're not familiar with this, the place to look is in this pink shading, which are the cold stadials associated with the so-called Heinrich event, iceberg discharges. I'll say a little bit more about them. But in a way, those are the coldest times in the northern hemisphere. And if you look more or less carefully, you'll see that they are times where the southern hemisphere was warming. And at the end of them, the northern hemisphere warmed. And that's when the southern hemisphere began to cool. And I'll get to my punchline. I think that we are providing further evidence that this bipolar contrast was driven by internal dynamics, by the ocean and atmosphere, and I would say largely by the overturning circulation of the ocean, moving heat around the planet, not shifting the mean temperature of the planet.
Jerry, I'm sorry for interrupting so early, but...
Don't be sorry. I welcome the interruption.
Then you try to correlate. There is a clear signal that's in phase between the southern and northern hemisphere as well. Not seesaw.
The argument that it's in phase, I think, has to do with the fact that the transitions in temperature don't proceed at the same rate. Well, maybe I shouldn't put words in your mouth. Where do you think?
Well,
would you say that it's warm here and it's warm here?
Maxima are sort of close to each other in temperature, and the minima are sort of close to each other.
The maximum and the minimum are close to each other. That's fair enough. I'm going to argue that they are close to each other, but they are not the same. At the very end of the talk, I'm going to show some unpublished data that come from the Waist Divide ice core in Antarctica, which is an Antarctic ice core with Greenland-style resolution. And I'm going to make the argument that although you're right that it's warm here and warm here, what happens is that this warms, and almost immediately, but not immediately, almost 200 years later, the south starts to cool. That's the point. And maybe they're certainly not anti-phase. That's not the argument that I'm making here. So we can come back and revisit that. But at least the contrast in the direction of warming and cooling can be described as a bipolar seesaw. That there's a shift in that cooling in the north is associated with warming in the south. And one means to accomplish this in a computer model is to flood the North Atlantic with fresh water. And this has been demonstrated again and again in a wide range of models. It's not the only way to make it happen, but it's one way. And the ocean circulation that I'm talking about is the large-scale, sometimes called thermohaline circulation, that just because of the accident of the shape of the basins and the fact that there's deep water formed in the North Atlantic, in the Atlantic Ocean, it's largely meridional. So that on some scale, there's a net northward flow of warm, salty water that's balanced by a deeper and somewhat colder water mass. So that's giving a heat transport northward. We know that that was different at times in the past. I'm going to argue that it was different again and again, and in almost exact conjunction with that bipolar evidence from ice cores. But before I get there, I have to introduce a few concepts. I've talked already about these Heinrich event iceberg discharges. This is what they look like in terms of evidence on the seafloor. This is the abundance of coarse detrital grains off the Rockall Plateau in the northeast Atlantic that almost certainly can only have arrived at these sites by drifting ice. And there are geochemical tracers in them that indicate that they came from North America, not from Europe. And what you can see here is this is the benthic oxygen isotope that tell us that this was the descent into the last ice age, and here's the last glacial maximum, and then the deglaciation. And you can see that the amount of debris in this sediment core doesn't increase monotonically or in concert with the amount of ice, but is repeatedly episodic, that there are layers after layer of debris. And the idea is that this is the debris that we find on the seafloor, but the conceptual model is if it came from icebergs, those icebergs melted, and in that melting, they would have lowered the salinity at the sea surface, therefore stabilizing the water column, diminishing the likelihood of deep water formation. So that's the background context about what might be going on in the North Atlantic. And now I'm going to present evidence from, in particular from a single new long core recovered from the Bermuda Rise, but it's going to be 3 lines of evidence about the deep ocean circulation. The Bermuda Rise is a feature that sits here in the deep western North Atlantic. Because of recirculation gyres, it has a tremendously high accumulation rate of sediment on the seafloor. And that allows better resolution of time in the past, but it's also presented a problem because it's too much sediment to capture easily in standard coring technology. The proxies that I'm going to use are sedimentary burial fluxes, in particular the preservation of calcium carbonate, which is a building block of microfossils on the seafloor, the burial on the seafloor of that calcium carbonate. A tool called protactinium-thorium ratio, which is based on the contrasting chemical behavior of uranium and its daughter isotopes in the ocean. And the third one is the stable carbon isotope ratio in benthic foraminifera that live on the seafloor, not within the mud. So before I get to the first proxy, I have to remind you that the Bermuda Rise is a deep location. It sits at 4.5 kilometers in the deep western Pacific, and you can see here in this map of dissolved carbonate ion that it's within this tongue of water that spreads southward as North Atlantic deep water and has a dissolved carbonate ion concentration that's right around 100 micromoles per kilogram, whereas waters spreading northward from the south have lower dissolved CO3. And that's relevant to the preservation of calcium carbonate on the seafloor because there is a pressure effect on the preservation or dissolution of calcium carbonate. This particular line here is the functional form of that pressure effect. So you can see that this is the saturation horizon, and that means that concentrations that would fall to the left of that would lead to increased dissolution, and concentrations that fall to the right of this curve would lead to an enhanced preservation. And I think it might be subtle, but I think you can recognize here, this here to here is the signature of that same North Atlantic deep water, whereas waters that are coming in from the south today at this location at about 20 degrees south, they're below the calcite saturation. So they're not preserving waters, they're corrosive waters. And I'm going to show that in the North Atlantic, that changed through time. I'm also going to talk about protactinium thorium, and so at this site map, I'm just putting you in the context of the global distribution of protactinium thorium. But I'll introduce that proxy in a little greater detail. The core we're using is one of 7 that were taken as part of a cruise of the United States' only long coring system, which sadly is going away because the ship that it's on is being retired. So I think possibly as I speak, that system is having its last run in the Atlantic. But these are some of the best cores that exist in the world for length, for quality, for volume, and preservation of the sediment without coring artifact. And you can see of these, there are recognizable wiggles in this density profile as measured on shipboard. And we chose to work on the core that had the longest continuous section with, by a small amount, the highest accumulation rate. And that means that we're looking at the last large climate cycle deposited in 30 meters of sediment on the seafloor. The benthic oxygen isotopes that we use to tell us where we are in time over this interval are quite recognizable, that they match well the global record of oxygen isotopes that show that here is the last glacial maximum, here is the current Holocene interglacial, here is the last peak interglacial, and here is the penultimate glaciation. And most of what I'm going to talk about is this interval here. So this is work that Bill Curry and his students at Woods Hole accomplished before Bill left for BIOS. They measured planktonic oxygen isotopes in every centimeter of the upper 20 meters of this core. That is, yes, something like 20,000 analyses. And from those individual measurements, a mean record can be mapped out that follows the Greenland ice core Delta 18. In the uppermost sediments, Jean Henry, a student at Lamont, has also measured in detail the composition of all the sediments. And what you can see for the last 20,000 years, going back to the last glacial maximum, is that the detrital composition and the calcium carbonate largely trade off. So the predominant sediment is always detrital material that's swept in from the continents and then remobilized. So it's very fine material. And then there's a mixture of calcium carbonate. The two of them trade off, but there is a third component of biogenic opal. So Jean did a great job on this, but it was a lot of work to measure each of these samples. And we were looking for a way, a more a rapid way, possibly less invasive, that would allow us to get data from all of the core. And Gene then turned to scanning XRF, which is X-ray fluorescence. And he analyzed the core by X-ray fluorescent at Woods Hole, and then used a calibration set of his own detailed measurements. And this is what the calcium carbonate content, the calibrated calcium carbonate content of that. This is the deep sea sediment core, and here again is Greenland. And it turns out, to our eye at least, that calcium carbonate oscillations and oxygen isotope oscillations occur in almost one-to-one correspondence throughout this cycle, throughout the length of this core. And if we blow this up, we can see that the times of low calcium carbonate content, this is just a percentage, are the Heinrich event intervals, and high calcium carbonate content are the warm interstadials over Greenland. But what we want to know is not the proportion of calcium carbonate, but its flux into the sedimentary record. And that flux can be driven by biological productivity, but this is the Sargasso Sea. It's a subtropical gyre. It's not a particularly productive place. We think that what controls burial here is the preservation on the seafloor. So we'd like to know the burial fluxes to get an assessment of the proportion of burial or preservation. And the way to get at that is to use a constant flux proxy. We know that uranium and its daughter product thorium have very contrasting behavior in seawater. Uranium is highly soluble, and that means that it has a long residence time in the ocean, on the order of hundreds of thousands of years. And because the mixing time of the ocean is some very few millennia, that means that the ocean is well mixed with respect to uranium. And that means that the decay of uranium into thorium at any one location is known, predictable, and relatively constant over the time scales we're talking about. Thorium, on the other hand, is essentially insoluble. And its residence time in the ocean, at least in the Atlantic Ocean off our shores, is on the order of a decade. It's produced, and it's removed rapidly by absorption onto settling particles. So that means it's accumulating on the seafloor at a constant rate. And in a schematic view, thorium is produced in the water column and then scavenged by a reversible exchange is the preferred model, but it's scavenged by adsorption and desorption and then adsorption again onto settling particles. And when there's a lot of sediment, that thorium-230 is diluted, and when there's not so much sediment, it's not so diluted. Either way, we can normalize the settling flux of anything accumulating on the seafloor. Now, because thorium is present in detrital materials, we have to make a correction for the material washed in off the continents, and we can do that in two ways. We do it by measuring as a ratio to so-called common thorium, or 232 thorium, or more directly by looking at the decay chain of uranium-238 and 234. Those isotopes occur in the Bermuda Rise at something of a constant ratio, so the two corrections yield the same result. And this is what thorium-230 looks like across that interval in the last ice age. This is all of the thorium-230 in the sediment. This is the excess portion, the portion that was absorbed by particles from the seawater. And when we invert for the settling flux of particles across this number of carbonate cycles, you can see here that there are changes in both the detrital flux and in the calcium carbonate flux. I'll first show the detrital flux. That's the predominant one, right? And what you can see is at the increase of each of these carbonate cycles, there's a spike in detrital flux, and then it declines. A smaller one here, another one here, a larger one here, and it declines. And the mass flux pattern of calcium carbonate is somewhat different. It tends to spike at about the same time, but it stays high longer. So in the end, the peaks in the calcium carbonate content are driven by both, but it's the increase in flux of calcium carbonate that we're interested in here. This suggests that across each of these events, calcium carbonate preservation at the seafloor was at a maximum. Yes?
When you say the concentration of the carbonate, what is the particle size that you're actually comparing?
It's everything. It's the bulk sediment.
You don't see any variation in the particle size of the carbonates?
There are variations in the particle size, and that's a function of the abundance of foraminiferal shells, which are sand-sized, versus coccoliths, which are silt-sized. But the calcium carbonate, yeah,
as carbonate.
Yes, because in the case, to get the high-resolution long record, that was generated by a remote method. That's X-ray fluorescence. It doesn't distinguish between those types.
Right.
And there's probably an important story there, but this holds here. So this is combining those figures now, and the carbonate percentage is in here, but I want to make the point to you that the peak in the detrital flux generally coincides with the rise of the calcium carbonate flux. In the end, I'm going to interpret both of those things together, and that's why I said sediment fluxes, not just calcium carbonate flux. We think that across each of these intervals, calcium carbonate preservation became better. Not that productivity increased to this great extent. Preservation became better. To us, that means that the dissolved carbonate ion increased at 4.5 kilometers of the deep sea. At those times, the detrital flux of fine-grained terrigenous material also increased. And we think each of these things is consistent with a flushing into the deep ocean of newly formed northern source water that had higher carbonate ion, as it does today, and remobilized sediments. We previously published the most recent of these spikes, and we speculated then that it might be remobilized detrital material or something related to rising sea level, because it was during the deglaciation. And the rising sea level might have remobilized sediment from the shelves. That can't be true here. These are not associated with those kind of large sea level changes. We think it's the remobilization of fine-grained sediments by the deep circulation. Okay, I'm getting to the second proxy. I have no feedback about my timing. Am I doing okay? Just give me a little high sign to speed it up if you can. I'm going to talk about the sedimentary protactinium thorium now. So the first told us, I think, a little bit about dynamics, more about the chemistry on the bottom. Protactinium thorium, we think, has the possibility to tell us something about You can think of it as the mean residence time of deep waters in the Atlantic Basin. And it's the same contrasting chemical behavior that we take advantage of. Uranium, in all its isotopic forms, is highly soluble. Therefore, it's well mixed, has a long residence time in the ocean, decays with a predictable and well-known rate to thorium, which is removed on the time scale of a decade, and protactinium, which is the daughter product of the less abundant uranium-235, but there are very, very few places on the Earth where uranium-235 and 238 don't occur in the same ratio. And the deep ocean is not one of them. They're both well mixed in the deep ocean. So these two are produced at a known and essentially constant ratio, but protactinium-231, while relatively insoluble, is not so insoluble as thorium. So it has a residence time that might be a century or even 2. That's time enough for lateral motions of seawater to move protactinium around. And those lateral motions can be disorganized, eddy diffusivity, if you will, or organized, advection with the deep water. Either way, the time scale is such that removal of protactinium is more possible than thorium. So what we can do is look at the sedimentary ratio of the two and compare that to the known production ratio. And the idea is if there is an organized flow, as there is today in the deep Atlantic, more of the protactinium can be swept away. And the observation is that in the North Atlantic, more than 90% of the thorium can be accounted for. It's being buried in the North Atlantic. And about half of the protactinium is missing. It's going somewhere. And that somewhere almost certainly is the Southern Ocean, which has high ratios of protactinium to thorium. Maybe the one number worth remembering within this talk, if not after the talk, is the production ratio of those two. This is an activity ratio that they're produced in seawater. It's 0.093. When the burial ratio is lower than that, it means protactinium is in deficit. When the burial ratio is higher, as it is in the Southern Ocean, that means protactinium is being exported from somewhere else. And within the Atlantic Basin, they're more or less in balance. Protactinium missing from the North Atlantic is being buried in the south, in the Southern Ocean. That behavior can be used to model the residence time of the seawater within the basin. And I'm not going to try to put a number on that, but the scaling is such that the residence time is longer when the protactinium-thorium ratio is higher, is nearer the production ratio. And the residence time of water must be lower when more protactinium is being exported and the ratio is lower. And across roughly the same interval of the last ice age, these are the protactinium-thorium ratios. So you can see that at the times when it is warm in the northern hemisphere, the ratios are lower. And these ratios reach numbers, they're going down, but they reach numbers, graphically anyway, that rival the modern observation that half the protactinium is missing. And that's in the context of an overturning circulation that's moving maybe 20 spherodrops of North Atlantic deep water out of the basin. So those appear to be the strongest overturning. During the cold times, that ratio increases, and in some cases, even rivals the production. Those intervals suggest longer residence time of the seawater and greater burial of protactinium locally on the seafloor. Now there are potential other ways to get values that look like this, and they mostly have to do with the scavenging intensity, and that's partially why I'm using multiple proxies here, because scavenging intensity is not going to affect some of the other ratios. But the most effective scavenger for protactinium is biogenic opal. Biogenic opal doesn't discriminate between thorium and protactinium and scavenges them both. And at the Bermuda Rise, there is at most a very weak relationship between biogenic opal flux and protactinium thorium. In other parts of the ocean, in other intervals of time, there's a very, very strong relationship of these two. But across how any of the definition of these intervals or the mean, there's at most a weak relationship. And so we think that scavenging is not the dominant process here. The relative strength of the lateral transport, which we think is related to circulation, versus scavenging. That's the control. Okay, the third of the proxies is a water mass tracer. It's not so much to do with the dynamics. It's not so much to do with particle scavenging and lateral motion. It's the signature of the water mass. And simply put, there is a relationship between nutrient content and stable carbon isotopes in deep waters. It's an inverse relationship, as phosphate or nitrate is utilized because of the fractionation, the selection of carbon-12 by photosynthetic organisms, not the conscious selection, but the preferential uptake of carbon-12 by those organisms. Essentially, all organic matter is depleted in carbon-13, and so when surface waters use up all the nutrients, they become highly enriched. The water that's left behind becomes highly enriched in del C13. And that prevails in the waters that sink as North Atlantic deep water, and to a much lesser extent holds for southern source water. So that in the modern ocean, in the modern Atlantic, this is the distribution of carbon isotopes. High here in the north. The end member for North Atlantic deep water is on the order of 1 per mil in del C13. Southern source waters are much lower and can get to 0 and even negative. And in a series of measurements in sediment cores from along the western margin, Curry and Opos showed that at the last ice age, the distribution was quite different from the modern. That this northern source water filled less of the basin and was only the dominant source in the upper 2 or 2.5 kilometers, whereas the deep basin was filled from the south. Now remember, these are the southern waters are the same ones that I showed had lower carbonate ion and were more corrosive in the modern ocean.
Sorry, is there some difference about the sources for those two water
Yes.
masses?
Okay, I'll spend a couple of minutes on this. Thanks for asking that question. It could be a longer topic, but the control there is when the water is subducted at either end of the planet, has its nutrient content been fully utilized? And in the North Atlantic deep water, the answer is closer to yes. And in southern source waters, whether they're derived directly along the Antarctic margin or by the upwelling of water that includes North Atlantic deep water that has had remineralized material. The upwelling in the Southern Ocean, rapid cooling and sinking. In either case, for southern source waters, the answer is much less yes and more like only partially. So that means that southern source waters, by the predominant mechanisms in the world today, that might or might not have been different in the past, but I would say are likely to have been the same. Antarctica was still there. The wind was still blowing over the circumpolar current. The physics that drive the changes today still prevailed. Nutrient utilization in the northern source waters leads to higher del C13.
Has it spent longer in the euphotic zone?
In part because it has spent longer in the euphotic zone. If you think of it as a conveyor where waters move through the South Atlantic, across the tropics, up the Gulf Stream, into the Norwegian current, you know, that's almost certainly the wrong way to think about it, but conceptually, that's a long residence time at the sea surface. Waters that form around Antarctica, first of all, upwell with high nutrient content. They may be shielded from the atmosphere by sea ice. They may gain their density properties subsurface by brine rejection of ice formation around the Antarctic margin, or they may come up to the surface, cool rapidly, and sink. In all of those cases, they haven't had a long residence time at the sea surface. So, you know, that would be maybe a shorter way to describe it. And we don't know that those things prevailed in the past, but there are reasons to think that they might have. Okay, what I was saying is that in the modern ocean, these southern source waters are more corrosive, and it's for the same reason that they have lower del C13. They have higher nutrient content, they have, more importantly, higher dissolved CO2, and unless they have equivalently higher alkalinity, they're going to have a lower dissolved carbonate ion. So this scenario would suggest less preservation in the North Atlantic. And this scenario, in the modern, suggests greater preservation. And those carbonate cycles that we saw, we interpret as shifts back and forth between these two. And this is what those carbon isotopes look like. When the protactinium-thorium ratios shift to lower values, the carbon isotopes shift to higher values. It's consistent with greater flushing from the north at the same time as nutrient depleted, high del C13, high carbonate ion, in other words, calcium carbonate preserving waters. All of these proxies are telling a coherent, consistent story. Then during the cold intervals, here, these smaller ones, but for example, this Heinrich event interval, these ratios approach the production ratio of protactinium and thorium, and at a time when the del C13 reaches a minimum, which in this case is minus 0.6. Now there's a whole ocean change in carbon isotopes, so we can't scale these exactly to the modern, but these are dramatically lower values. Even correcting for the whole ocean transfer of carbon from the terrestrial biosphere to the ocean, there's no water that looks like that in the Atlantic Ocean today. These look like great incursions from the south. And then what happens immediately afterwards is greater export of protactinium, greater preservation of calcium carbonate, and higher del C13. And this next figure summarizes all of that. Although shockingly poorly on the big screen. You can all come up and look at my computer one by one, because you'll see the difference here is some clarity of the labeling, but more importantly, maybe some shading at each of these cold intervals. This is the one I was just talking about, right? That, and here, here, here. In any case, I'll trust you to guide your own eye. Our argument is that the calcium carbonate content is driven by changes in calcium carbonate flux. And remember, our preferred interpretation of that is not big changes in productivity in the subtropical gyre. They're big changes in preservation. And those coincide with the presence at depth of high C13 water that in the modern ocean forms in the north and has lower nutrient content, lower dissolved CO2. And those are times here where the protactinium-thorium ratio decreases. That's the top panel. That suggests shorter residence time of the northern waters. They're less stagnant, they're moving laterally, and our preferred interpretation is that they're moving laterally in a systematic flow from north to south as part of the AMOC. Now, this is the summary of what I've just been talking about. I'm going to show briefly 3 snippets of evidence that are separate from this and are either related or follow on. The first is what I promised at the beginning. With the permission of Christo Bouzert and the Waste Divide Ice Core community, I'm going to show some of their unpublished results from the ice core in West Antarctica that has an Antarctic signal but higher accumulation rate that allow really detailed comparison with Greenland. And the same structure or the same approach to that alignment prevails here. And that is the fact that methane concentrations are well mixed throughout the atmosphere. And therefore, methane in Antarctic ice cores and methane in Greenland have to vary at the same time. But the structure of that variation looks very much like the northern hemisphere. So these things can, the methane structure allows the cores to be aligned. And you see this same pattern here. Now, sorry, time is moving from the left to the right because the Waste Divide Ice Core community and others in paleoclimate are thinking maybe we have to communicate with the rest of the world, not just with each other. There are some who resist that, but I think communication is a good thing. But once you flip your mind around to where you're normal, and maybe when you walked in, you can see that same pattern. Rapid warming in the north. This is the rapid warming in the north, cooling in Antarctica. And in their careful analysis of the phasing of those things, they arrive at this conclusion. Greenland changes first, and then a century or two later, Antarctica changes. That's both for the warming in the north, which is then followed by cooling in the south, and cooling in the north, which is then followed by warming in the south. And I would argue that this is consistent with those changes in the Atlantic meridional overturning circulation playing a role in the bipolar connection, because the time scale of that mixing in the Atlantic Ocean is on the order of a couple of centuries. So the communication of that signal down the length of the Atlantic might begin initially, but it would be fully realized after a couple of centuries. I think that there's something like 3 to 5 year nominal. You know, they don't know the age of each piece of ice, and what's most important here is not the true chronological uncertainty, but the relative uncertainty in the sequence. But I think the nominal resolution is some few years. Because they take chunks of ice and measure them. I suppose this is jumping around a little bit, but this is that last Heinrich event during the last deglaciation, where we've now generated and compiled something like a depth transect down the length of the Atlantic, and the relevant transect is actually all in the North Atlantic. And the implication here is that from the last glacial maximum, which had something of a diminished overturning, into the Heinrich event that occurred during the deglaciation, the overturning circulation in the Atlantic diminished. And that signature is felt throughout the water column. And this was the most recent, no, that's not quite right. This is the most recent but one event that the waste divide community looked at. This is the so-called Heinrich event 1, and there's one more event after this, the so-called Younger Dryas, and we don't have this kind of data set there. But this is additional evidence, I would say, that the overturning circulation played a role during the deglaciation. And then the last question is, if, maybe this is a big if you believe that these changes punctuated the entire last glaciation and the deglaciation, have they been occurring through the Holocene? Are these kind of dramatic changes part of the climate system at all time scales? And we're just beginning to explore this. But the initial evidence, at least at the resolution that we've currently achieved, is that we don't find evidence for such dramatic changes. In the previous figure, this is the deep western basin. This is actually very near the deep western boundary, and there's not any signal of strong oscillation. There's a deficit in protactinium at all times. It looks like the export of protactinium from the North Atlantic has continued throughout the Holocene. So I'll wrap up by saying that the changes in the AMOC accompanied the abrupt climate changes during the last ice age. This has been postulated for some time. There is some evidence existing that would support that. We would say that we provide further evidence for that again and again. The deep Atlantic repeatedly filled with the equivalent of North Atlantic deep water that was vigorously produced. And when that happened, dramatic warming ensued in the north and cooling began in the south, although the ice core records now tell us that those things weren't synchronous. That the warming happened in the north, and some century or two later, cooling began in the south. So I would agree with this concept of a bipolar seesaw and suggest a change in the spelling. That's all. Thank you.